Hello everybody, thank you for having us. My name is Todd Wagner and I am the Project Manager and Water Resources Engineer with Vector Associates. Today we're here to talk about our progress so far on the Crown Point Business Park expansion. So today's presentation includes a few steps. We broke it down a little bit. We're going to talk about the project overview. What are we designing as a whole? Then each of our engineers is going to have a chance to talk about their individual projects on this larger parcel and how they all relate to each other. Finally, we're going to have some time for some questions. So, what are we designing? We've got 4 different things going on this large parcel. We're first building a road that's connecting this western Maryville Road with North Indiana Avenue or East Summit Street. Then we're designing roadway drainage and a storm sewer system. That would be the environmental engineer's duty. Then we're designing a multi-use structure, and we got a few different alternatives for that structure. And finally, we're designing the water resources for a specific parcel on this larger site. I'd like to hand this off to our transportation engineer.
Thank you, Todd. Hi everyone, my name is Leah, and I am the transportation engineer with Vector Associates. So I was tasked this semester with examining the current condition of our 52-acre plot of land in Crown Point, Indiana. And from there, I want to assess the current traffic conditions and roadway usage at that southeast corner, which is the intersection of Summit and Indiana Avenue. And then from there, I want to develop alternatives to see, once our structure is developed, how can we best accommodate that incoming and additional traffic at that intersection. And from there, I want to evaluate the cost and alignment choices. So I've done probably about 75% of that so far this semester, where I have drawn the existing geometry from the CAD files we were given by Dr. Algebay, and I've created 2 different alignments and profiles in Civil 3D using the existing contours. And from the typical section in the Crown Point jurisdiction technical standards, I have drawn that on Civil 3D, and from there I was able to run a traffic impact study using the Vistro software, and I developed 3 different alternatives for intersection and 2 different alternatives for alignments. So my typical section I drew up based on the jurisdiction of a local road. As we know, that's about 30 miles per hour for a local road is the speed limit. And from there we're going to have 12-foot lanes, 5-foot sidewalks, and we're going to have like about 2.5 feet of gutter space. And we're going to have a 2% slope given the Crown Point design standards. So my first alignment, if you can see, even though it's a little cut off over here, goes from northern side of Maryville Road to the, that's Indiana Avenue over there, and it has a pretty equal cut and fill profile. If you were to draw a line like this, it's about 5 on top, 5 below feet wise, so that's pretty even cut and fill. And one of the benefits of this alignment is that it does not intersect with any like existing gas lines or any existing roadway lines or anything like that. And the 2 yellow lines right here are our existing power lines, telephone lines, and so both of my proposed alignments will have to go under those as it is unavoidable. My second alignment has a very similar cut and fill profile, probably a little bit more fill on this one, but very similar elevation. And this alignment connects from Maryville Road to Summit Road down here. But what's not shown in this is that there's gas lines and an old existing train tracks that are no longer in use, but they still are there in the ground. So that would be harder to develop over top of, and for that, it has led us to propose most alternatives based on my first alignment. Okay, so now we're going to look at the southeast intersection, which is the Indiana Avenue and Summit Street, taking north as the upward direction in all my photos from here on out. So by using the ITE design manuals provided by Dr. Grossman, we were able to classify our building as 20,000 square feet of a general office building and then 20,000 square feet of a business park. Our structural engineer will talk a little bit more about that later. But from there we were able to run models and figure out which direction will have most additional trips. And our phase 1 will develop 27 trips, and that's with just our 1 parcel of land developed. So that's 1 structure developed. And phase 2 is when all additional trips, so that was doing our whole 52-acre land, dividing it by our 1.89 acre parcel, and that would be a factor of safety of 28, so 27 times 28 is about 745. So we're going to design for saying all the parcels in our plot are developed. And from there, I developed 3 alternatives on what to do with the intersection. So designing for phase 2, if we do nothing at all, and when we have all phase 2 done, we have a level of service F, which indicates that we'll have 121.4 seconds per vehicle delay. That's over 2 minutes. I was a driver, I would not want to sit there for 2 minutes just waiting to turn right or even go through. So that's if we left it as currently with his 1 left turn lane and 1 right and through lane combined. My second alternative is to separate that through lane and that right lane on all approaches, and that gets us to a level of service of C, which is what INDOT, which is the Indiana Department of Transportation, wants. And C is good. And that would be a little under 30 seconds of delay, and as a driver, I would probably be okay with that. But if we wanted to go a little bit more, my second alternative is to add an additional through lane and an additional right turn lane, which does increase intersection very wide, but it does accommodate for a level service B and an under 20-second vehicle per delay per vehicle. And so with those alignments, my next work will be having to evaluate those based on cost and the current lane conditions, knowing that whenever you add lanes, you're probably going to have to cut into existing land, and that's a lot of other local landowners that might not be happy with you, so I will have to figure that out, and by drawing that, I will be able to see which land will be cut into, and I will do that using Civil 3D, and from there, I'll be able to pick which alignment and which intersection is our top choice. I now want to pass it to our environmental engineer.
Thank you. Hello, I'm Maddie, and I am the environmental engineer for Vector Associates. My scope for this project was to create a pavement drainage system for the proposed road going through the Crown Point Business Park. This includes developing alternatives for inlet configurations, as well as for the conveyance system type. I will then be following the design standards from the Crown Point Stormwater Technical Standards, as well as HEC 22's Urban Drainage Manual, and then of course following local, state, and federal regulations. My preliminary calculations so far have included determining the inlet spacing for the proposed road. So this is an example using Leah's first alternative road. I first determined the runoff rates on each of these sub-watersheds using the rational method, and then I also determined the spread across the road and the depth of ponding on each of these sub-watersheds. These are very important standards to follow because you cannot have a spread too wide and you cannot have deep ponding because those will cause road accidents. And then the spacing is also determined by the interception capacity of the different inlets. This example was using great inlets, so most of the spacing is around 125 feet or less. Things to note on this specific road, according to the topographic profile, there are 2 low points where the conveyance system for the pavement drainage can connect to the subdivision's stormwater management facilities. There's also 1 high point near around the existing power lines. And 2 big assumptions that I made for this delineation is that the only contributing areas to the pavement drainage come from the sidewalk areas and the road areas, and that the crown of the road will create a divide as well, which is why you can see that there is a line in between that essentially splits the road in half. The alternatives that I've analyzed so far are the inlet configurations. So our first type of inlet are great inlets. These are efficient at intercepting sheet flow, and they can be used on a wide range of gutter slopes. However, they are prone to clogging from trash and debris, and in areas of high bicycle traffic, they need to be designed to be safe for bicycles to pass over them. The second inlet alternative are curb opening inlets. These are more efficient at handling high amounts of debris, and they are safe for bicycles. However, they are more efficient on flat slopes and in sag inlets, which are low locations, so they are not as efficient over steeper gutter slopes. And the final inlet alternative are combination inlets. These combine the advantages of both grate and curb opening inlets, so they are available to use over a wider range of slopes, and they can handle larger amounts of debris. However, they are more expensive and more complicated to install. My future progress will be the preliminary design of the conveyance system alternatives. This will include a sewer piping system as well as different types of swales that are along the roadway. I will then be doing an alternatives analysis, including a cost estimate and using our selected system criteria to select the most effective alternatives for this design. I will now be handing it off to our structural person.
I'm Emma Hickey and I'm the structural engineer for this team. My first job is to come up with the building site location and the orientation of it. I'm still talking with Todd on where exactly we want to place this building in terms of drainage, but we have come to the conclusion that we will place it in the northwest corner of our plot of land. My most important task is to come up with 3 alternatives for a structural design of a mixed-use building. In order to do this, I need to find the loadings that would be needed in the different uses. I need to determine the types of materials I want to use, and I need to come up with interior floor plans that take up 40,000 square feet and coincides with the purpose of the building. After that, my steps will be to come up with a cost estimate and then evaluate my alternatives based off the design criteria that we have came up with to pick the best one. Starting off with the materials, I chose to stick with steel and concrete. The most common types of steel have a yield strength of 36 KSI or 50 KSI. The most common type of concrete is a normal weight of 150 pounds per cubic feet, and this will be reinforced with a grade 60 steel bar. Here I've come up with some loads from CEE 7 that will be represented when talking about the use of the building. And then down at the bottom, I found more information about the snow, wind, and seismic loads from the CEE Hazard Tool 2. My first alternative is a one-level steel structure. This structure will be for industrial and office use. As you can see, I put some individual offices down at the bottom, and then more space for the employees, like a break room and conference room at the top. I chose to leave the middle completely empty as I want this to be more of like a warehouse. My next step for this alternative is to come up with a layout for the beams, girders, and columns. As I said before, I want this to be open so that there's a lot of space for all the trucks and equipment, which means I want to refrain from using columns here. So I chose to design this with steel because steel is very durable and it can allow long span lengths. But with these long span lengths, the beams will be very thick. So I actually think that the best thing to do here is to use trusses in the framework. An advantage for this alternative is that there are a few industrial buildings surrounding this plot of land, so it actually will fit well with this area. A disadvantage of this alternative is that it is just huge and it takes up a lot of land. My next alternative is a 2-level steel structure. This structure will be for commercial and office use. Each floor will be 20,000 square feet. The first floor will have 3 commercial spaces that are all relative in size, and the second floor will have 2 office spaces that do reflect each other. I would like to point out that there are staircases so that you can get to the office space without having to enter the commercial space. For this one, I have been able to come up with a layout for the beams, girders, and columns. Like I would like to put the columns, even though that they're not an issue for this one, I would like to still hide them within the wall, so I try to match it with the interior floor plans of both levels. For this one, it is still steel, but the span lengths will be much shorter, so the beams will be thinner. And then the spacing of the beams, it is common to be from 8 to 12 feet. So I use 10 feet on some of them and 12 feet on others, but I try to make a consistent pattern throughout the whole structure. An advantage for this structure is that it is 2 levels, so it will take up less land, and steel tends to be easier to work with when designing. My last alternative is a 2-level concrete structure. This structure will be for commercial and residential use. Each floor will be 20,000 square feet again, so it does look very similar to the last alternative, but it's made out of concrete this time. The first floor has 3 commercial spaces again, but the difference is now the staircases are on the ends, so that when you go in and then you turn, it kind of matches with the hallway of the upstairs. The second floor is a residential space, which has 10 apartment suites. I chose to make this one out of concrete because concrete is fire resistant and that seems much more safer when talking about residential spaces. I've also been able to come up with the layout for the beams, girders, and columns for this one. The interior floor plans of both levels made it difficult to hide the columns in this one, but I still think it's okay that a few columns are showing. And then as you can see, all of the spacing of the beams are 10 feet here throughout. An advantage for this one is that it's 2 levels, again, so it takes up less land. And concrete requires less maintenance in the future. Some things I still need to work on is coming up with a cost estimate using RS means. I'll use the square footage from the interior floor plans that I've come up with to come up with this cost estimate. Like I mentioned before, I still need to come up with the beams and girders and columns and now trusses layout for the 1 level alternative. And then my last step is to evaluate all of the alternatives to come up with the best one to continue my work on. Now handing it off to our water resources engineer.
All right, thank you, Emma. So on the water resources side of things, the client has requested 3 different things for my design. First thing is that I need to treat the water. And that includes any water that runs off the site needs to be reduced in total suspended solids by 80%. So that means I need the solids to settle out using some form of BMP. And I also need to reduce the amount of nitrogen in the water. This is going to reduce the likelihood that eutrophication happens in the area that I discharge this water into. Next thing I need to do is infiltrate 1 inch of runoff. So of the water that falls on the site, 1 inch of that needs to be infiltrated into the groundwater supply. Next, I need to regulate the flood control volume. So that's how much of the quantity of the water is leaving the site. And I decided to break this up using a couple different ways. So to achieve those things that I just said, we first needed to decide where is this parcel going to go. So looking at the entire site, we decided to choose a localized high point, which is in this northwest area. This high point means that there's going to be no off-site water running onto our site. So that way we can just design for the water that falls onto our parcel. Next thing I need to do is combine some of Emma's alternatives and Leah's preliminary parking lot sizes onto this site. And that's where I developed 4 different alternatives for this parcel. And next thing I need to do is do a quantitative and qualitative analysis of those 4 parcels. So let's take a look at them. My first parcel places Emma's 2-story structure on the left side and places Leah's parking lot on the right. I have a detention basin in the northern area, which is where all the water is going to be directed towards using vegetated swales and a lot of land grading. That water is going to be discharged into the wetland using that green vegetated swale in the top right corner. As you can see, each one of these alternatives has a time of concentration line, which is this blue line, and I have potential areas where I can put BMPs, such as a rain garden, which you'll see throughout this project. Alternative 2 uses Emma's single-story structure. This structure takes up a lot of space. There's a lot less pervious area here, and that's going to be shown when I do my analysis in a little bit. Again, the detention basin for all of these is going to be in the northern corner, so that way all the water can be captured and discharged in a single area. My third alternative places Emma's 2-story structure in the middle. This leaves me with a lot of space. I got a lot of room for these BMPs. We can put rain gardens to capture potentially any runoff from the roof structure. I can put a rain garden here to capture any runoff from that parking lot. And again, all that water is going to be funneled towards this detention basin where TSS can drop out. My fourth alternative places the structure laterally. Again, this is Emma's 2-story structure, and it leaves a little bit less area for these vegetated swales. However, there's some area up north where I could potentially put a BMP. So let's see what the numbers have to say. In my quantitative analysis, I developed a composite curve number for each of these sites. From that, a time of concentration, and I was able to calculate a flow using that detention basin's inlet as the design point. This assumes that all water that falls on the site gets funneled into that design point, which is my goal. That's why there's vegetated swales on the outside to direct all that water to that one area. And so when you look at the numbers, we want to look at which alternative has the lowest storage volume. This means that my facilities that treat this water are going to be the smallest, because a smaller storage volume is going to be more cost effective. So alternative 3 wins here. It has the small storage volume, so that's what I like the best right now. And all of my equations were from the Stormwater Technical Standards manual. Next up is my qualitative analysis. What amount of water do I need to treat on the site? And this is again using equations from the Stormwater Technical Standards manual. Again, alternative 3 has the most pervious area, and as a result, it's going to allow me to have the least water quality volume to treat. So how do I actually treat that water quality volume? I'm currently going through some best management practices alternatives. I'm going to be doing a very similar process to what I did for these site plans. I'll be creating spreadsheets, looking at equations, and analyzing the costs. Some of them that I have in mind right now are the vegetated swale, which is really good for removing total suspended solids. I have a biofiltration system with an upturned elbow. This is going to create an area with anaerobic and aerobic nitrification, which is going to remove nitrogen from that water source. Also, the detention basin itself allows for total suspended solids to settle out. And vegetated filter strips, if you place them before these BMPs, they can gather things like trash and total suspended solids. And so each of these comes with a cost, and I will also be looking at cost analysis for all these BMPs. So, other than that, thank you guys for listening, and we would now like to answer any questions you have. Yes.
What challenges have all of you come across on this so far?
Okay, so far, interpreting the Stormwater Technical Standards Manual document. So just a lot of time looking at that, really trying to understand what the client is trying to follow here and really being diligent in my calculations following the guidelines.
On the transportation side of things, using the NDOT road viewers and seeing the annual traffic, the data was last collected in 2018, which in all things traffic, we know COVID had a huge play, so having road numbers and traffic counts from 2018 is not very accurate, so we had to find other ways. So actually a lot of our traffic numbers are actually interpreted from our advisor, Dr. Grossman. So.
As far as the environmental work, having to read through HEC 22, it's a lot of equations and a lot of new calculations for me, so this has been a new design that I'm learning while we go.
For the structural standpoint, the one-level structure is very large, and trying to come up with something that leaves that space open so there aren't any columns. Professor Reich, and she explained the trusses, but still my next step is to understand it and then come up with the third plan.
Yes.
Okay, let's go technical a bit in here. Can start with Maddie. Maddie, you mentioned that your design or the sub-warsheds is based on the water spread and the ponding depth in there, and I'm assuming that you are either using the NDOT or Indiana Stormwater manual or the HEC 22 manual in there. So what are the criteria in this case? So how much of a spread across the road are you allowed, and what is the maximum ponding depth of the stormwater before you decide on where to locate your inlets?
So the maximum spread across the road, I believe for local roads, you have to allow one lane of traffic to go through. So I estimated that to be around 6 or 7 feet, determining that based on Leah's road, because I can't remember. I think I said 7 as my maximum because it's 7 feet around each side, so that allows for one lane of traffic to pass through. And then the depth of ponding maximum is 7 inches according to the Crown Point technical standards.
Okay, good. Todd, you mentioned that you want to direct the flow towards the wetlands. Are you allowed to do that? Are you allowed to discharge runoff from a parking lot or the roof or the building or a lot into a wetland?
I cannot find anything that said that these were protected wetlands, so I'm assuming yes.
Okay. I'll go with your answer, but the typical answer is no.
Okay.
So that's a violation actually in there. And on the second layout, I think that's maybe goes to you and Emma at the same time. I'm seeing your building is so close to the lot boundary line in the
Mhm.
over here. Did you guys look at the setbacks allowed by the ordinance? And so how far away from the lot lines you need to be?
I did not look at those ordinance, but I did notice that these were coming very close, so this is probably an alternative that we're not gonna go with. Also, it yielded the highest, like, storage volume, so we're not gonna go with alternative two likely.
And I don't know how much time I have, but I will go maybe back to Emma in there. In the table of loads, you are listing the dead load. Is that dead load a constant for any type of material? If it's a steel structure or a concrete structure or?
No, the roof dead and the roof live load, those ones can change, but those were the maximum ones that I had come up with. So I thought those were more important to include than the minimum ones, but it will change with steel.
And how did you get the snow loading of 50 pounds per square foot?
From the CEE hazard tool, when you put in the location, it tells you.
Okay. I'll accept that. Okay. Do I have time? Oh, okay, go ahead.
Todd, when you said a number of times that you're choosing one alternative because of the .21 versus .26 acre feet. How big a difference is that?
I looked it up,
Don't
it's
give me
about
percent
like,
stuff, I mean, like, is it as big as the, how big a deal is that? Or is that really close?
these are all somewhat close, it's just, why choose one when you could choose less? It's gonna be more cost effective for the client, even if it's just by a little bit.
So you're, at this stage, you're simply going on size.
Yeah.
Is your alternative.
Yeah, and it happened to be that alternative three was one of our favorites when me and Emma were putting it together, and Leah, because there's just a lot of space around it, so I could put like BMPs like to all sides of the structures if I want to. There's room to extend the parking lot for Leah, and then, yeah, there's just a lot of wiggle room, so.
And I'm guessing that at this stage, this is kind of just a picture. The building is not gonna be exactly there. The parking lot hasn't been laid out exactly right.
Yeah, the building is gonna be there, and it's got Emma's dimensions on it and everything. The parking lot's more subject to change than anything, so.
I had a question for Maddie also. You're talking about the sub-watersheds.
Yes.
Could we go to that slide? I couldn't see them.
That's
I don't
okay.
know.
That might have just
Maybe you
been
could
the
just
picture.
explain that to me
Yeah,
or
it's
something.
this.
I don't know if I can point it out very well. So each sub-watershed, they're mostly rectangular, so it's extending from.
Oh, and there's a little red, is there red in there?
Yes.
Well, see?
So it's extending from the center line of the road to the edge of the sidewalk area.
Okay. Yeah, I didn't see those.
And then do the catch basin locations basically determine those watersheds? Is that why they're broken up like that? or-
Yes.
Yeah.
So the catch basins for example, for this top sub-watershed, the catch basins will be along that boundary there. So then bypass flow will go on to the next sub-watershed, but that's calculated separately from the base flow of that sub-watershed.
Okay. And then, since you're there, you mentioned that your alternative three for the catch basins, the combination
Yes.
is most expensive.
Yes.
Is that like the material cost or to install, or, and what didn't seem to me that would be that much more expensive, so what makes it more expensive?
It is just expensive because it's more materials. I have not looked into installation costs
Okay.
yet, but I will. But generally it is because it is two different components instead of
Okay.
just one.
Okay. And then I had a question for Todd.
Mhm.
So, like, it looked like all your alternatives are different building sizes, different layouts, but your stormwater BMPs are they always vegetated swale, rain gardens, and a detention pond?
For the sake of this study, yes. So this was
Okay.
mainly for just finding out which which collection of buildings and placements of those buildings is
Okay.
best for the like water quality volume and
Okay.
best for the storage quality volume. These are more so like my rain garden typical, that's mainly just to show like it could be placed here, could be placed there.
Okay,
But yeah, each one of these is, yes, they're all pretty much the same. And then
Okay.
I'll be doing a study with different BMPs to treat this water quality volume, which is what I'm currently looking at.
yeah, so you're gonna have multiple different BMPs and comparing their
Yes,
effectiveness? Okay.
exactly.
And that's gonna be done by the?
That'll be,
technical-
that's for the memo one.
Yeah, yeah,
So
okay.
I'm like halfway through that right
Okay.
now.
That's good, thanks.
Alright. All good? Thank you.
Yep, thanks.